the P-47 Thunderbolt pilots became some of the most successful P-47 aces of World War II within the European theater alone. This remarkable achievement wasn't just about pilot skill, it was the result of groundbreaking engineering that created one of the most formidable fighter aircraft of World War II. At the heart of the P-47's success lay its innovative P-47 engine and P-47 turbocharger system, which allowed it to operate effectively at altitudes above 30,000 feet. The aircraft's engineering represented multiple technological breakthroughs, from its massive R2800 double Wasp engine to its advanced structural design that could withstand extreme combat damage. This video examines the extraordinary engineering decisions and technical innovations that made the P-47 Thunderbolt a masterpiece of aviation design. From its revolutionary power plant to its robust weapons systems, every aspect of the P-47's design pushed the boundaries of 1940s aerospace technology. Engineering marvel, the P-47's revolutionary design. The Republic P-47 Thunderbolt stood as a testament to ambitious engineering, emerging as the largest and heaviest single-engine fighter of World War II. Its development pushed the boundaries of aeronautical design, creating an aircraft that would become legendary for its combat effectiveness. The Thunderbolt's massive frame was unprecedented for a fighter aircraft of its era. At 5 tons before loading fuel, bombs, and ammunition, it dwarfed contemporary fighters. The aircraft's empty weight matched or exceeded the maximum loaded weight of other fighters. This extraordinary size wasn't a limitation, but rather a calculated design choice, allowing for robust internal systems and significant combat capability. The P-47's design team, led by Alexander Kartveli, faced unique aerodynamic hurdles. The most significant challenge came from integrating the massive turbocharger system, which was comparable in size to a small washing machine. The solution was revolutionary. The engineers designed the duct system first and built the fuselage around it. This unorthodox approach resulted in an efficient airflow system that maintained high performance at altitudes above 30,000 feet. The aircraft's structural design was an impressive achievement in innovation and engineering. It featured a semi-monocoque construction made entirely of metal, utilizing a stressed skin approach. This design incorporated transverse bulkheads and longitudinal stringers to distribute structural loads efficiently, ensuring durability and aerodynamic efficiency. Central to its robust design were 2 main wing-supporting bulkheads built around steel beams with an E-section profile, each measuring 3.5 inches wide. One of the most notable innovations was the telescopic landing gear. When retracted, this system shortened by 9 inches, a clever engineering solution that reduced drag and allowed for optimal positioning of the aircraft's armament. This careful integration of systems underscored the attention to detail in the aircraft's design. Advanced materials played a pivotal role in the airframe's construction, showcasing the collaboration of various specialized manufacturers. The Aluminum Company of America provided essential aluminum components, including alclad skin, which offered a combination of strength and corrosion resistance. The American Magnesium Corporation supplied specialized magnesium alloys, particularly for the engine cases and wheels, contributing to the aircraft's lightweight design without compromising strength. Numerous subcontractors from the Northeast and Midwest industrial hubs also played a crucial role, fabricating specialized components that brought the aircraft's innovative design to life. The structural integrity of the P-47 proved exceptional in combat conditions. Its robust design allowed many aircraft to return to base despite sustaining significant damage. The wing design, featuring a distinctive semi-elliptical shape, provided both structural efficiency and convenient space for the heavy armament installation. This engineering marvel demonstrated that size and weight weren't impediments to creating a high-performance fighter aircraft. The key lies in the precise balance of power, structural strength, and aerodynamic efficiency. The success of these engineering solutions was evident in the production numbers. Republic Aviation Corporation manufactured over 15,200 Thunderbolts, achieving a peak production rate of 28 aircraft per day. Power plant engineering. At the core of the P-47's exceptional performance lay its power plant engineering, which combined the mighty Pratt Whitney R200 double Wasp engine with an innovative turbocharger system. This engineering marvel began development in 1936, setting new standards for aircraft engine capability. The WWII double Wasp engine was an engineering masterpiece, featuring 18 cylinders in a double-row radial configuration. Each cylinder displaced more volume than an entire Toyota Camry engine. Key specifications included: displacement 45.9 liters, power output 2,000 horsepower at 2,800 rip, weight 1,068 kilograms, bore and stroke 146 mm x 152 mm. The turbocharger system represented perhaps the most complex engineering feature of any American single-engine fighter. Located approximately 22 feet behind the propeller, the turbocharger system utilized an intricate network of ducts and cooling mechanisms. The system's efficiency was remarkable. NACA studies showed the R2800's efficiency increased from 28% to 33% with the turbocharger integration. The exhaust gases traveled through carefully designed collection rings for each cylinder bank, routing through shrouded piping to the turbine. This innovative design allowed the P-47 to maintain peak engine power across a wide range of altitudes, unlike contemporary fighters with fixed-ratio superchargers. The cooling system featured multiple innovative components working in harmony. The intercooler system utilized a sophisticated air routing design, with cool ambient air traveling through the main duct intake under the engine. This air passes through the intercooler to reduce the temperature of the compressed air from the turbocharger before reaching the carburetor. Temperature regulation was achieved through electrically controlled doors on both sides of the fuselage, which adjusted the cooling airflow. The system included 2 oil radiators mounted below the engine, featuring surge valves that allowed cold oil to bypass when necessary. This comprehensive cooling solution enabled the engine to maintain optimal operating temperatures despite generating tremendous heat from its high power output. The integration of these systems required extensive ducting. Intake air traveled a total of 43 feet from the nose scoop to the turbocharger and back to the injection carburetor. This complex arrangement, while challenging to engineer, proved highly effective in combat operations, enabling the P-47 to maintain high performance at altitudes where other fighters struggle to operate effectively. Advanced materials and construction. The construction of the P-47 Thunderbolt marked a significant advancement in aircraft manufacturing, combining innovative materials with groundbreaking assembly techniques. Before loading any combat equipment, the aircraft's base structure weighed 5 tons of precisely engineered materials. The P-47's construction relied on a strategic combination of lightweight yet durable materials. Alcoa supplied the crucial aluminum components, including specialized tubing and alclad skin panels, while American Magnesium Corporation provided specialized alloys for critical components like engine cases and wheels. The material selection included aluminum alloys for primary airframe structure, high-strength steel for load-bearing components, magnesium alloys for wheels and engine components, and 24-Saint alloy for control surfaces. The aircraft featured a semi-monocoque all-metal, stress skin construction with an innovative approach to load distribution. The fuselage incorporated transverse bulkheads and longitudinal stringers, creating a robust structural framework. 2 main wings supporting bulkheads, each constructed around 3 1/2-inch wide E-section steel beams, formed the backbone of the design. The wing structure employed a full cantilever design with 2 main spars and stress skin construction. Engineers incorporated varying web thicknesses, ranging from 0.032 inches for outboard sections to 0.250 inches for the inboard forward main spar. This graduated approach to material thickness optimized weight while maintaining structural integrity. Republic Aviation Corporation revolutionized aircraft production methods, establishing 2 dedicated factories that produced over 15,200 Thunderbolts. The production process was an extraordinary feat of industrial collaboration, relying on a vast and intricate network of specialized suppliers. Each partner brought unique expertise and capabilities to the table, ensuring that every component met the exacting standards required for the Thunderbolt. Shakeproof Incorporated played a vital role by supplying advanced anti-vibration hardware critical for maintaining structural integrity and performance under the stresses of combat conditions. Liquidometer Corporation contributed essential fuel and oil tank measuring devices, providing pilots with precise readings to manage resources effectively during missions. Meanwhile, Huber Manufacturing delivered specialized equipment used in the production facilities themselves, enabling Republic Aviation to streamline and enhance the assembly process. The construction process incorporated innovative assembly techniques, including the use of extruded angles for frame installations and flanged ribs secured between spars at precise intervals. This approach allowed for efficient production while maintaining the exceptional structural integrity required for combat operations. The manufacturing innovation extended to the control surfaces, where engineers developed all-metal tails after discovering that fabric-covered surfaces could experience ballooning at high speeds. This modification, along with other structural improvements, enhanced the aircraft's performance in high-speed combat scenarios. Combat engineering features. Survival in combat drove the engineering priorities of the P-47 Thunderbolt, resulting in an aircraft that could withstand significant damage and protect its pilot in the harshest combat conditions. The robust design helped create many P-47 aces of World War II by giving them the confidence to engage in intense aerial combat. The P-47's armor protection exceeded that of any contemporary fighter aircraft. Engineers installed a face-hardened 3/8-inch armor plate at the forward and aft ends of the cockpit. The cockpit's upper section featured one 1/2-inch bullet-resistant glass, providing comprehensive protection for the pilot. This extensive armor placement proved crucial in ground attack missions, where the aircraft frequently faced intense anti-aircraft fire. The fuel system incorporated advanced safety features essential for combat survival. Two primary self-sealing fuel tanks featured sophisticated baffle systems to minimize fuel surge during aggressive maneuvers. Engineers equipped both tanks with electrically operated booster pumps, ensuring reliable fuel pressure even if the main engine-driven pump failed. This redundancy proved vital in combat situations where maintaining engine power could mean the difference between survival and disaster. The P-47 Thunderbolt's reputation for survivability was not solely due to its robust armor and self-sealing fuel systems. It also benefited from an array of advanced redundant systems that enhanced its resilience in combat. Among these, its electrical network stood out as a critical feature designed to ensure the reliability of essential systems, even in the face of significant battle damage. The electrical system's redundancy played a pivotal role in maintaining the operational integrity of several key components. This design safeguarded engine ignition systems, ensuring that power delivery to the engine remained uninterrupted, even if portions of the network sustained damage. Similarly, the aircraft's communications equipment relied on this redundancy, allowing pilots to maintain contact with ground control or other aircraft during missions of vital capability for coordinating operations and ensuring safety. Additionally, the turbosupercharger controls, a cornerstone of the P-47's high-altitude performance, were bolstered by the redundant electrical system. This feature enabled the Thunderbolt to maintain its exceptional power and climb rates even in adverse conditions. The air-cooled engine design provided superior combat survivability compared to liquid-cooled engines. While a single hit to a liquid cooling system could disable an engine within minutes, the P-47's engine could continue operating even with significant damage to its cooling system. The aircraft also incorporated an internal belly skid structure, enhancing survivability during emergency landings. The heavy construction that characterized the P-47 provided additional benefits in combat. Its substantial weight contributed to increased diving speed and enhanced resistance to battle damage. This robust engineering approach proved particularly valuable in the ground attack role, where the aircraft regularly faced intense enemy fire. The P-47's ability to absorb significant combat damage and return home became legendary among pilots, with many aircraft surviving despite sustaining massive structural damage. Weapons system integration. The engineering marvel of the P-47's weapons system centered around its formidable array of 8.50 caliber Browning and M2 machine guns. This powerful armament system helped create numerous P-47 aces during World War II, establishing the aircraft's reputation as a lethal aerial platform. The P-47's wing-mounted armament consisted of 8 M2 Browning .50 caliber machine guns, with 4 guns installed in each wing. This configuration delivered approximately 13 pounds of lead per second, surpassing the firepower of contemporary fighters that typically carried only 6 guns. The engineering team designed the gun placement to optimize weight distribution and maintain the aircraft's balance during combat maneuvers. Key specifications of the weapon system included: combined rate of fire 100 rounds per second, individual gun capacity 425 rounds, muzzle velocity 2,900 feet per second, total ammunition capacity 3,400 rounds. The engineering team developed an innovative staggered design for the ammunition feed system. Each gun was positioned approximately 1.50 caliber length behind the adjacent weapon, allowing for efficient side-by-side ammunition box placement. This configuration enabled balanced weight distribution across the wing structure, efficient spent case and link ejection from the wing's bottom, and optimal ammunition feed reliability during high-G maneuvers. The ammunition system accommodated various combinations of rounds, including armor-piercing incendiary, and armor-piercing incendiary tracer. A 5-second burst from all 8 guns could concentrate 500 rounds into a 3 feet x 3 feet target area at 1,100 feet range. The fire control system utilized electrical solenoids controlled by a trigger switch mounted on the control stick. This system provided synchronized firing of all 8 guns, reliable operation in various combat conditions, and quick response time for target engagement. The integration of the weapons system required careful engineering considerations for the wing structure. The main landing gear featured a unique 9-inch shortening mechanism during retraction to accommodate the outboard guns. This innovative solution maintained the aircraft's aerodynamic efficiency while housing substantial firepower. The weapons system's effectiveness was further enhanced by the aircraft's stable platform characteristics. A standard ammunition load provided approximately 20 seconds of sustained fire, giving pilots sufficient engagement time during combat missions. The system proved particularly effective in both air-to-air combat and ground attack roles, contributing to the P-47's versatility as a fighter-bomber. Flight control systems. The sophisticated flight control systems of the P-47 Thunderbolt represented a complex integration of hydraulic power and mechanical innovation that enabled precise aircraft control even under extreme combat conditions. These systems proved crucial for P-47 aces of World War II, providing the control precision needed for both dogfighting and ground attack missions. The P-47's hydraulic system powered multiple critical aircraft functions through an integrated network of components. Key elements of the system included a primary landing gear retraction mechanism, a flap actuation system with a 40-degree range, brake control systems, gun charging mechanisms, and a flap equalization valve. The landing gear featured an innovative telescoping mechanism that shortened by 9 inches during retraction, optimizing space utilization within the wing wells. This design incorporated a sophisticated sequence valve system that coordinated the retraction cycle with precision timing. The control surface design emphasized durability and precision. Engineers developed the elevators as individual units, joined through specialized torque tubes extending from their inboard nose sections. This configuration provided enhanced control authority while maintaining structural integrity during high-speed maneuvers. Equally advanced was the aircraft's flap system, which incorporated a range of forward-thinking features to optimize performance across various flight conditions. The flaps were hydraulically actuated, enabling pilots to adjust their positioning incrementally up to a maximum of 40 degrees. This variable positioning capability allowed for greater versatility during takeoff, landing, and combat scenarios. The hydraulic system also ensured smooth and reliable operation, with a full deployment cycle completed in just 11 to 15 seconds, a rapid response time that was crucial in dynamic aerial engagements. Additionally, the P-47 was equipped with specialized compressibility recovery flaps, a groundbreaking feature designed to address the challenges of high-speed dive recovery. At extreme velocities, particularly during dives, aircraft could encounter compressibility effects that compromise control. These flaps were specifically engineered to counteract such effects, restoring stability and allowing the Thunderbolt to recover smoothly from dives. This innovation not only improved safety but also enhanced the aircraft's tactical capabilities, enabling it to engage in aggressive combat maneuvers with reduced risk. The cockpit design prioritized functionality while maintaining pilot comfort. The spacious cockpit featured a sliding hood with emergency jettison capability. Engineers positioned instruments and controls for optimal accessibility, though the layout appeared complex to pilots transitioning from other aircraft types. The control interface of the P-47 Thunderbolt was a testament to its sophisticated engineering, incorporating several advanced systems to enhance pilot functionality and aircraft performance. The throttle quadrant was designed with an additional lever specifically for controlling the supercharger, allowing pilots to manage engine performance and maintain power efficiency across varying altitudes. This added control was critical for the Thunderbolt's ability to excel in high-altitude combat. The aircraft also featured electric controls that managed essential cooling mechanisms. These systems allowed precise adjustment of both the intercooler and oil cooler shutters, ensuring optimal engine temperature regulation under a wide range of operating conditions. This capability not only improved engine efficiency, but also contributed to the aircraft's overall reliability during extended missions. Equally innovative was the flap control system, which was equipped with an equalization valve. This design feature ensured symmetrical deployment of the flaps, maintaining aerodynamic balance and stability during critical phases such as takeoff, landing, and combat maneuvers. The supercharger control system offered two operational modes. Pilots could either link it to the throttle for unified operation or operate it independently at altitude. While the linked configuration provided smoother operation, it resulted in heavier control forces than typical fighter aircraft of the era. The hydraulic system's reliability proved crucial during combat operations, with redundant systems ensuring control surface functionality even under battle damage. This engineering approach contributed significantly to the P-47's reputation for bringing pilots home despite sustaining severe combat damage. Performance optimization. Engineering excellence manifested in the P-47 Thunderbolt's remarkable performance capabilities, which made it one of the most effective fighter aircraft of World War II. The aircraft's optimization focused on three critical areas: high-altitude performance, speed-weight balance, and combat maneuverability. The P-47's high-altitude capabilities set new standards for fighter performance. The aircraft could maintain 412 mph at 34,000 feet, demonstrating exceptional high-altitude effectiveness. This performance stemmed from its sophisticated turbocharger system, which enabled the engine to maintain optimal power at extreme altitudes. The aircraft's high-altitude capabilities were further exemplified by its maximum speed of 429 mph, achieved at 27,800 feet, and its proficiency in conducting effective combat operations above 30,000 feet. Even under the demanding conditions of reduced air density, the P-47 sustained high-speed performance, making it an invaluable asset in engagements requiring altitude supremacy. These characteristics underscored the Thunderbolt's reputation as a high-altitude powerhouse, capable of outperforming many adversaries in this challenging domain. Despite being the heaviest single-engine fighter of World War II, the P-47's engineering team achieved remarkable speed performance. The aircraft demonstrated varying speed capabilities across different altitudes. At sea level, the Thunderbolt could reach 345 mph. As it climbed to 10,000 feet, its speed increased to 3838. At 20,000 feet, the aircraft could sustain 417 mph, eventually reaching an impressive 435 mph at 32,000 feet. The engineering team addressed weight challenges through innovative solutions. Water injection systems could temporarily boost engine output to 2,800 horsepower, enabling the aircraft to achieve 1 horsepower per cubic inch of displacement. The P-47's combat performance relied on specific engineering solutions that maximized its strengths. The aircraft excelled in high-speed diving attacks, utilizing its weight and power to execute effective boom and zoom tactics. This approach allowed pilots to maintain a superior altitude position, execute high-speed diving attacks, use momentum to zoom climb back to safety, and minimize exposure to enemy fire. The engineering team optimized the aircraft's dive characteristics through careful aerodynamic design. The P-47 could achieve diving speeds of 550 mph, making it one of the fastest diving aircraft of the war. This capability proved particularly effective when P-47 aces of World War II employed bounce and zoom tactics against enemy fighters. The P-47 Thunderbolt's performance optimization extended impressively to its climbing capabilities, a critical factor in both combat effectiveness and tactical flexibility. Engineered to excel in vertical maneuvers, the aircraft demonstrated exceptional climb rates, even at its substantial weight. At military power settings, the Thunderbolt achieved an initial climb rate of 2,305 feet per minute at sea level, a testament to the power of its turbocharged radial engine. This robust climb performance allowed pilots to gain altitude rapidly, an essential advantage in securing air superiority or positioning for an attack. The aircraft's operational ceiling reached a remarkable 40,400 feet, underscoring its ability to operate effectively in the upper limits of the combat envelope. This high service ceiling not only expanded its strategic range, but also allowed it to engage adversaries at altitudes where many other aircraft struggled to perform. Time to altitude metrics further highlighted the P-47's climbing efficiency. It could ascend to 20,000 feet in just 11.6 minutes, a feat made possible by the combination of its advanced turbocharger system and powerful engine. The engineering team's focus on high-altitude performance paid dividends in combat scenarios. The P-47's ability to maintain high speeds at altitude allowed it to set the terms of engagement, particularly when operating above enemy aircraft. This advantage proved crucial for escort missions, where the aircraft could effectively protect bombers while maintaining tactical superiority. Water injection systems further enhanced combat performance, allowing for temporary power boosts during critical moments. This system could provide up to 5 minutes of enhanced power output, giving pilots crucial advantages during intense combat situations. Engineering evolution. The development journey of the P-47 Thunderbolt traced its origins to the innovative designs of Alexander P. de Seversky in the early 1930s, evolving through multiple iterations to become one of the most effective fighter aircraft that would create numerous P-47 aces of World War II. The P-47's evolution began with the AP-4 demonstrator in 1939, powered by a Pratt Whitney R1830 radial engine with a belly-mounted turbocharger. The initial XP-47 billion featured all-metal construction except for fabric-covered tail control surfaces, marking a significant step in the aircraft's development. A pivotal moment came when Alexander Kartveli, recognizing the limitations of earlier designs, completely reimagined the aircraft's architecture. The design team kept the basic cockpit layout while stretching the fuselage and reshaping the tail surfaces to accommodate more powerful systems. This transformation resulted in what would become the largest single-engine fighter of World War II. The P-47's capabilities saw significant enhancements through several key modifications. Each successive model of the P-47 demonstrated notable advancements in speed, climb rate, and overall performance. The P-47D, an early production variant, could achieve a top speed of 435 mph at 32,000 feet and had an initial climb rate of 3,180 feet per minute at sea level. The P-47M brought significant improvements, reaching an impressive 473 mph at 2,000 feet and an initial climb rate of 3,960 feet per minute. The P-47N, with a top speed of 457 mph and a climb rate of 3,580 feet per minute. Several innovations contributed to these improvements across the P-47 series. The integration of a water injection system was a key development, allowing the engine to generate bursts of additional power when needed. This system temporarily increased engine output, providing critical advantages during combat or high-demand scenarios. Upgraded versions of the Pratt Whitney R2800 engine were another cornerstone of the Thunderbolt's performance evolution. These enhanced engines delivered greater power and reliability, ensuring that the aircraft could operate effectively across a wide range of altitudes and mission profiles. Fuel capacity was also increased in later models, enabling extended range and endurance, particularly critical for operations in the expansive Pacific theater. The P-47N, for instance, was equipped with larger internal tanks and provisions for external drop tanks, making it well suited for long-distance escort and ground attack missions. The introduction of the bubble canopy was another transformative improvement, offering pilots unparalleled visibility. This design eliminated the framing of earlier canopies, providing a clear, unobstructed view that enhanced situational awareness in combat. These advancements solidified the P-47 Thunderbolt's reputation as a versatile and powerful fighter, capable of adapting to the diverse demands of aerial warfare, while maintaining its edge against evolving adversaries. Republic Aviation Corporation implemented innovative manufacturing processes that dramatically improved production efficiency. The company established multiple production facilities, achieving remarkable output rates. The P-47 Thunderbolt's manufacturing process introduced several groundbreaking approaches that enhanced efficiency and consistency. Specialized tooling was designed specifically for mass production, streamlining the assembly of complex components. Standardized assembly procedures were implemented, ensuring smooth, efficient workflows and uniformity across production lines. Additionally, robust quality control systems were developed to maintain consistent standards throughout the manufacturing process, guaranteeing that every aircraft met the required performance and durability specifications. The evolution of the P-47 demonstrated the rapid advancement of American aviation technology during World War II. Early production models underwent continuous refinement based on combat feedback. Engineers addressed initial challenges such as cockpit smoke issues, which were traced to oil drips, through systematic improvements. The aircraft's development cycle showcased the iterative nature of wartime engineering. When aerial combat reports from Europe in 1940 indicated the need for a breakthrough design, the Republic proposed a fighter that exceeded all contemporary specifications. This responsiveness to combat requirements led to continuous improvements in the P-47's capabilities. Production optimization reached its peak with the introduction of specialized manufacturing techniques. The complex turbocharger installation, which required the air to travel 43 feet from the nose scoop to the turbocharger and back, demanded precise manufacturing tolerances. This engineering challenge was met through innovative assembly line procedures and quality control measures. The evolution of the P-47's design reflected a deep understanding of combat requirements. When the German Fu-190 began threatening the P-47's edge in 1942, engineers responded by adding water alcohol injection to the R-2800 engine, bringing it to peak power output using new high-octane fuel. This adaptation demonstrated the aircraft's ability to maintain a competitive advantage through continuous improvement. Manufacturing efficiency improvements enabled the Republic to maintain high production rates while incorporating design changes. The addition of press paper wing tanks, bubble canopy, rocket tubes, and bombs on the wings and belly represented significant manufacturing challenges that were successfully overcome through optimized production processes. The engineering team's commitment to continuous improvement extended to every aspect of the aircraft. Post-crash analysis revealed that the complex duct system, initially seen as a potential weakness, actually formed a protective cushion between the pilot and the ground during accidents. This unexpected benefit exemplified how thorough engineering analysis could yield multiple advantages from single design elements. The P-47 Thunderbolt is a remarkable achievement in wartime engineering, combining innovative features like the powerful R-2800 double Wasp engine and advanced turbocharger system for exceptional high-altitude performance. Its impressive speed, diving capabilities, and maneuverability pushed the limits of 1940s aerospace technology, making it effective in both air-to-air and ground attack missions. The P-47's legacy continues to inspire aviation enthusiasts, showcasing how innovative engineering can overcome size and weight limitations. What do you think made the P-47 Thunderbolt stand out among other fighters of its time? Share your thoughts and experiences with this iconic aircraft. If you enjoyed this video, Don't forget to like and comment. Thanks for taking the time to watch the video.